Hello, does this work now? Can I have it? Working? Hello? No? Can I have this also working? Okay. Hello, everybody. I hope you had a nice dinner, and we are ready to start with the rump session. But before this rump session, we have a very important thing to do to give the Test of Time Award. And this is the ceremony for CHES 2024. I had the honor to be the chair of this small committee to decide on the Test of Time Award for this year. Just to give you an idea what this is and how this procedure works. It has started since 2020, and we give a Test of Time Award for a paper with lasting impact in the field with respect to both academia and industry. And the award in year X honors a paper published at CHES or TCHES in year X minus 21, between X minus 21 and X minus 19. Any one of you, anyone from the community can nominate a paper. Usually the deadline is around May, June. You should check on the website. And the committee that decides is a rotating committee, which consists of 2 members that are appointed by the CHES steering committee. And then these 2 members choose 3 more members. We try to have members which are from the PCs of the years that we include in the current year for awarding. On this website, you can find all the information, and please remember, it's very important that you nominate your favorite papers, because if you don't get nominations, of course, we cannot award. This year, this was the committee. We had 3 PC members from CHES 2004 and 5, because these are the years actually that we were considering. And Amir and me were, Amir was the one appointed by the steering committee, and I was chairing it. The deadline was 1st of June, and we received 4 papers nominated from 2004 and 2005, the conference in 2005. And the award goes to a paper from CHES 2004, which was held in Cambridge, Massachusetts, and it was chaired by Marc Joie and Jean-Jacques Wiscotter. And here are some quotes from the nominations that we got, that it became the standard analysis to conduct evaluation. So as you can guess, it's a paper about attack that had a huge impact on the practice of side channel attacks and evaluations. It's a primary attack that any side channel practitioner uses. It's a paper that everybody has read, and had 3,000 plus citations. I just want to say a few words how we were choosing the papers. We didn't only look at number of citations, because we think this is a very, it's not everything about papers that we publish. We were looking at 3 main criteria. What is the academic impact, what is the industry impact, and eventually some standardization that has been connected with this paper. So it goes to this paper. This is the abstract. Maybe some of you can guess which one it is. If not, I can give you a bit more hints. The authors are from GemPlus. The people in the audience which are a bit older remember this company, which has been acquired later. And these are the authors. I guess it's already clear, but here is the title. So the award goes to correlation power analysis with leakage model. And we are very honored, one of the authors of the papers, to be with us here today. I'm inviting Francis to the stage to receive the award for all the authors, of course. Congratulations.
Thank you, Svetla.
This is the plaque that you get. Yes, 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 that's not everything. And there is a small present from the general chair with the paper and your names on, and with the S box, apparently, if you turn the AESS box, something nice to put on your desk. And now we will have a short presentation by Francis, which will come. Yes, please go to the stage and you will get your
the one. Here's the S-box. It's a broken S-box.
Thank you very much, Svetla. Before I enter this presentation, I'll just do some small historical and personal introductions to this award. But of course, I want to thank you very much for it. It's a problem not to be able to. Yes, thank you for the award. Just a few historical reminders, but before this, prior to this, I want to speak of the authors. I will start with Christophe Clavier, who is not there. He's not there because he has left the company at the time. The company name was GEMplus. We will pretend to be the leaders, the world leaders in the smart card industry. And he was a friend of mine before we started to work in GEMplus, and we were borrowing together in a software company. But I was not from the cryptographic community, but he was a passionate guy by the number theory, and he entered GEMplus in 1998 or 9, something like that. And there was just the year after the DPA crisis. And I was from acoustics and vibration. I was completely an absolute beginner, almost 40 years old at the time. And he told me, Francis, come in GEMplus, we need your help for signal processing and all these sorts of things. So I was hired in 2000, and then Eric Brie joined us again, a very brilliant guy. Time has passed in the meantime. Christophe has left the company 6 years after that, and Eric almost 1 year after, maybe. And I remember the upper management, and maybe some of you have heard about David Nakash, who was very famous in the community. And when he hired me, he told me, Francis, I want experts in the company. I want people who commit on long term. And they all left GEMplus, so 6-7 years later, when we merged with our first competitor, Axalto, to become Gemalto. GEMplus plus Axalto made Gemalto. And they all left the company, and here I am again. So I owe to Christophe Clavier to be here today. So it's a weird story because I was not from the community, and I feel very honored to be here tonight, thanks to them and thanks to all of you, of course. What about the paper? We introduced the acronym CPA after Paul Kosher has introduced the DPA a few years ago. But before we released the methodology, we said, well, we found something strange and we have to check before. In fact, the results are from 2001, but we are solution providers, so we cannot kill our own products, so we check everything before we release. We cannot, of course, we cannot release attacks. This is not our job. but we used to see a lot of things in the publications around during the technological survey, the conferences, and so on. And so we wanted to make things clear because there were a lot of noise, a lot of buzz all around. And so the idea of CPA is not very original. Using Neyman-Pearson linear correlation is quite a classical approach. Speaking of Hamming weights, of course, it's the same. And we have also heard about the transition model, the flipping bits, counting for the flipping bits in the process. This is not quite original, so we are not the inventors. We just made a synthesis and applied it to a real case on a real smart card. And out of this paper, we pulled, let's say, obvious things that look obvious today, but they were not at the time for us. The lesson number one was that the leakage is related to the process. And the leakage depends, of course, on those transition, but there are some hidden parameters. And this is what we found. These transitions can be related to static parameters or dynamic ones, and they depend on the architecture. At the time, the examples we gave were on a very simplistic smart card. The microcontroller was an 8-bit architecture, so something very simple. And of course, the implementation was not even the AES at the time, it was the DES. But this is interesting. So we found this sort of result that you cannot see anymore because we have real experimental correlation reaching 90%. That's quite impossible today, except with the simulations, of course, noiseless simulation. And what we learn out of this is that handling a single word, so the example was just a basic XOR operation between 2 bytes, 2 operands, very simplistic things. And we see that the very simplistic things can provide quite surprising results. You handle 1 word and you get 2 points of interest. And we realized that those points of interest were related to transition with opcodes, with addresses, all the same. And this was quite emotional to us because we didn't understand at the time a single thing about DPA. We observed the results, PX, hypothesis testing, but we could not understand how it could work. And now we had the idea of something like some kind of a model in birth, applying to our own implementations. And the second lesson, that's modeling is possible, and it is helpful, of course, for the attacker. And we showed this way that Hamming distance were better than the Hamming weights. And that was much better, of course, than single bit GPA. Paul Kocher, he has had opened a bridge a few years before. Of course, it was a very clever method to create a traumatism and propagate the psychosis in the industry. His paper was not really well written, but his patterns were very, very, very tough. And everyone fell into his patterns at the time. So he earned a lot of money thanks to this. So very well played from him. And then we had another issue, is that the issue was what we used to call at the time when addressing the deaths, the issue was the ghost peak problem. When we applied the DPA as in the Paul Kocher way to our own implementation, and we were not the only one to observe that. We had very bad results during the hypothesis testing. The right hypothesis didn't, and very often some other hypotheses came first. It was never well ranked. And they say, well, now we have something like a sound methodology to analyze what happens. We are conscious, we are aware that the process is complex and related to some internal things occurring inside. And maybe we could try and use this methodology to solve this ghost peak problem. And that's what Christophe and Eric did when they introduced the S-box model. And they were able to predict all the DPA biases for any kind of hypothesis. And even when you have the right one here indicated with the blue arrow, you can observe that it's maximum maybe in magnitude, but not in sign. And there are some positive peaks that maybe go higher in absolute value. And this was, of course, related to all the biases, the way we implemented the lookup tables, because you have 2 values per byte. So when you think your selection function is handling 4 bits of S-box output, in fact, you handle 8. The S-box are biased, not uniform, blah, blah, blah. So we got aware from this first experiment that things were most difficult, more complex than what everyone can imagine. And we wanted to share this experience with the community, of course. Sometimes, of course, this modeling is not really necessary for an attacker, but we, as defenders, we have to understand and to know our own weaknesses, and of course, in view of fixing them. Okay. Since then, what happened? Back to historical things. After the merging, there were a lot of big brains that left the company, unfortunately. Some of them, remember, they are here present in the room. And then it was another period. We entered another period. We were feeling like living some kind of heaven or golden age. All the brains, the main one were leaving the company, and we have less and less means to work. And we had to cope with some other attacks like fault attacks. And this was a very strange period because fault attacks are another kind of attack which are very, very aggressive against the smart card products, of course. By the way, I take the opportunity to say that after we turned into Gemalto, 12 years later, the company was bought by Thales. And the surprising thing is that Christophe, in the meantime, he became a teacher in engineering school in the University of Limoges. And Eric, he left the company to another company, and then he moved to Thales. And then Thales bought Gemalto. So we again belong to the same company, but I'm the only last rat from the laboratory is involved with higher activities. And I'm still a representative of the original laboratory. Technically speaking, what happened? We have been in the meantime aggressed by acronyms. Acronyms like, of course, SPA, GPA, CPA, of course, we introduced the acronym. But in the meantime, you know, all those acronyms like LRA, MIA, higher order things, and all the, the acronyms on the lower left part of this slide with the template attacks, machine learning, cluster analysis, and deep learning here. All those techniques were coming as avalanches of attacks against our products, and we had to, of course, to answer our customers. Are we able? Do you resist this new attack or not? And so on. Of course, we cannot implement them all, especially if you have budget reductions. But you have to think of something to do. Afterwards, of course, we resist quite well. And I don't speak of all the fault attack parts out of all of these techniques. All those analysis methods are very interesting because they all have pros and cons. and the pros of one technique is maybe the con for another, and vice versa. So they are very complementary to each other. For instance, if I consider MIA, which was introduced even in CHES more than 10 years ago, if I remember it well. I remember a paper by Benedict also to make it more comprehensive. And well, it's very interesting, especially for higher order analysis. But as a counterpart, you need a leakage model because you are doing some kind of a profiling when you analyze your data. So it's good for the one side, but what about the leakage model? You are still dependent on this. And all those techniques, the supervised attack methods like template, deep learning, and so on, are very interesting because they broadened the field of application of side channel attacks. So far, we were very focused on crypto libraries, and they show that, no, there are some other targets around crypto libraries. And today we have to deal with, of course, what I used to call static targets. Static targets are the targets like key scheduling or data transfers, simple data transfers from memory to memory. These are some new targets that we have to protect because our customers and the certification labs demand this out of our implementation. So how can we reply to all these methods? And what about now? I will speak only, even if we have some studies, some research activity regarding some other devices like FPGAs or system on chips, these sort of things. I will keep focused onto the smart card industry. What are the physical trends in smart cards? Of course, the semiconductor shrinking. We are now far below the micron for the elementary cell. We have faster clocks beyond 50 megahertz. Think that you know what a smart card is. It's a low-end product, something you live in your wallet, in your car, everywhere. Sometimes you lose it, and it's special crypto machines with very simplistic things and at the same time very sophisticated features. Of course, we have more complex architectures. There is no more 8-bit microcontrollers, of course, so they are at least 32 bits large with crypto accelerators and hardware security features. I hope that from yesterday's presentation that there's a lot of work done to implement masking, for instance, at the hardware level. And on top of this, of course, you have less consumption, so less signal and more noise, or at least a lower ratio, signal to noise ratio. That's the general trend. So it seems that the measurements are going to be more and more difficult, but you know what? The leakage remains. It remains, I should say, most of the time. I should mitigate this assertion because there are some very hard microcontrollers. Some of our providers have worked a lot to kill to treat the root causes of our leakages, and they have pretty good results. So the measurements are more and more difficult. And but some other remains, and also we have to say that, and we have in our labs, of course, taken advantage of all the advances in measurement techniques to improve the measurements, increase the amount, the precision, the bandwidth, and for the data. So things are more and more aggressive. Measurements are more and more difficult, but everything improves all the time. This is how technology goes. And the question for us is, do we generate new risks? So are we in the position of Don Quixote, who sees the windmills as the new giants, threatening giants, very dangerous ones. Should we be more paranoid or what? So we have to keep calm. And of course, we are pushed by the market, by the certification labs, all the actors of the industry that one has to protect everything, to put belts and braces. But we know that opening an umbrella indoor may have some disadvantages and drawbacks, and sometimes it's maybe dangerous, or it may be just for performances reasons, for memory. If you use too much memory because you put too much protection, sometimes we are blamed for giving too much protections, and the management says, well, but security does not sell. So we want money, we don't want security, we don't mind. And the customers, do they mind about this? And then we have the security crisis. So you have to cope all the time with this kind of debate. And of course, we need some methodologies to have to reply relevantly to the solicitations. Okay. A new thing is that we have some new threats, and sometimes these new threats are either unfortunate because we have residual bugs or mistakes or things which were not demanded. And the question we have is, can we live with those partial residual leakages, especially during memory transfers, this sort of operations, which are so simplistic. But sometimes we would like to protect them, and we cannot for many reasons. And the question is, can we live with these leakages? Of course, some people say, no leakage, we don't want any leakage. But it is there. How do you cope with it? And in fact, we need to address, of course, the question of the risk, the guessing entropy. And with these questions are all related to the let's say, the mathematical properties of the leakage. So like it's the surjectivity of the mapping between the data and the signal, the non-uniformities, the complexity, how many bits are leaking at a given time. And maybe with a sound guessing entropy estimation, if we are able to estimate the real, let's say, a tight interval for the guessing entropies, maybe we can live with this and let the wolf enter into the ship hold and turn him into Tantalus. That is, yes, maybe you can observe what's happening. Like Tantalus, you can see the fruits, like the leakage as a fruit, but you cannot pick them up because they are too complex and you cannot exploit them. And that's sometimes what we are facing as a new situation. Okay. As a matter of fact, to answer all those questions, I personally put a special effort to better model the leakages and understand the leakage and quantify and give some metrics for this. So we need modeling for this. The problem of speaking of a model is that it is an ambiguous word. What is a model? We speak of behavioral models, statistical behavioral models, when you speak of template attacks, for instance. But it is quite restricted to the classical Gaussian-based inference, almost restricted to 8-bit implementations due to complexity issues. Some people from the artificial intelligence have introduced their neural networks with deep learnings, the multi-layer perceptron and the convolutional networks also, neural networks. And when they have set up all the parameters of the network, they speak of a model, right? So very dangerous when when AI speaks of model, because AI, they have plenty of answers to many problems. You just have to find the problem. That's the issue. And they cannot help us in reverse engineering what happens, because they don't give any explanation. They give a response. It is 80% sure or not. We have a sensitivity, but you don't understand the things inside. So they are certainly not very helpful for this. We had a very interesting presentation yesterday by Google people about this, and we might have some debate about it. Personally, what I do personally prefer is the what I used to call the multilinear bit model. This is the one that has my preference. It was introduced by Werner Schindler in 2005 yeah. It wasn't, I don't like the name, he called it stochastic model. I don't like this name. It was also recalled linear regression analysis, but it's just a way of speaking of a basic linear combination of the bit bi that make a word, and you associate to each bit a physical weight, a piece of signal plus an offset called C0 plus noise, supposed to be Gaussian noise with variance sigma n square. And I like this because it gives a lot of information. Here are a few examples from electromagnetic analysis. When you look at this, so how do you estimate the coefficients? Either you have a pseudo-inversion matrix of a matrix system, or you can use basic bit DPA, just like Paul Kosher did. And it is very effective. It's very sound. And it gives you very interesting results about the leakage with, you can see an example here. When you have a leakage, you have plenty of points of interest. And when you give the bit breakdown, so the contribution of each bit within the signal, you observe this. They might be spread in magnitude, and it is quite astonishing. Sometimes some bit leaks 10 times more than the next. It's really surprising. There are, of course, various signs also, even if you use power signal. And on the zoom, on the right part, or on the right picture here, you sometimes can observe some difference in the time of arrival. So this is something to deal with the timing at attacks. The question is, maybe someday, if we have very high time resolution, we'll be able to separate the bits by that time of arrival. But you need very, very high, very large, very broad bands for that in your measurements. I mean, electromagnetic probes, preamplifiers, measurement chain, oscilloscope, and so on. And of course, everything goes quicker and quicker. So you have to imagine that the periods of the signal will be tightened and tightened and squeezed all the time. Okay. The advantage of this representation is that you can deduce out of it all kind of statistical indicators. There is a basic formula for all them, like correlations and covariances, everything. Even you can also conduct the hypothesis testing if you're addressing a S-box or something more complex, or let's say a 32-bit XOR, for instance. And thanks to this, you can have an assessment of the surjective mapping, the degree of surjectivity of the data to signal mapping. You can assess the presence or not of biases, and you can also, and above all, estimate the complexity, how many bits are leaking at a given time. This is the basic and fundamental question. So far, we have a lot of representation of 8-bit leakages given by template attacks, for instance, but we have to move beyond this because there is no more 8-bit architectures. Of course, we all have the bottleneck, 8-bit bottleneck of IAS box, But of course, you don't have only AAS to address. And to me, this is the first step towards a better guessing entropy assessment, to find a common metric and understand what is the level of the risk, associated risk. I have to conclude. I'll not be too long. Don't want to be too long. Just a few conclusions. So I feel a bit for prospective. I feel a bit embarrassed when compared with Mr. Brennel, of course. I should be, it's not the same level, of course. We still have open questions about the guessing entropy, rank estimation. We have the basic questions about noise. Everyone considers, it is widely admitted that the noise in our model is Gaussian. And as a matter of fact, when you consider this issue, it seems not. Probably because, of course, what is purely random might be due to the central limiter looking like Gaussian distribution. But you have all the modeling errors, which are due to numerical digital things. And these are probably not Gaussian. This is what we observe with the sort of little histograms here. You have some peaks, you have some holes, you have some chimneys in the distribution in the histogram. This is quite strange. So maybe there is something to do on this side. As far as understood, there is a presentation tomorrow on this special issue. If I have read the program well. And of course, we have all the future crypto systems to analyze. I observed that in CHES you are already addressing this issue, because I saw some sessions this afternoon about side channel analysis applied to post-quantum cryptography. Will the hardware be harder and harder? It seems that how long that the semiconductors are involved, they will keep on leaking. It's just a question of being able to measure them. Of course, we have more complex architectures, and modeling complex architectures is, of course, more difficult. Problem of measurability. And I don't speak of quantum computers, but here again, I thought that the principle of quantum mechanics were merely with the determination principle, were merely killed the notion, the basic notion of side channel, because it is based on measurements. And normally, as far as understood, measurement determines the state of the data.